The figure below represents a circuit in which a DC generator is connected to two storage batteries in parallel so that the latter may be charged. If the open circuit battery voltage are VA is equal to 108 volts and VB is equal to 110 volts, and the several resistances are as indicated on the diagram. Calculate IA, IB, and I. The total power delivered by the generator, the total power loss in the resistors, and the efficiency of the system. As you can notice, the current of the two batteries are not flowing out of the positive polarity. It's going the other way because it says in the problem that the DC generator is charging these two batteries. First of all, let's label some things and identify the node we're going to work on. Since the current is entering in this part of the resistor, it has a potential rise, making it a positive, and the other side a negative. Now let's look at the node here and see that it has three currents involved. So we'll use this for KCL. Again, the current entering is positive and current leaving is negative. Therefore, we have positive I, negative IA, negative IB equal to 0. Or we can write this as I is equal to IA plus IB. This is now our first equation. Since we have 3, we need 2 more to go, and we can find those using KVL. Now the loop we are going to trace is the small loop and the bigger loop in both clockwise direction. Let's start with the small loop, which involves these 3 components. So for VG, that's positive. I times R is negative because we are going out of this side. Now here we're going to write both the open circuit voltage and the voltage drop of the battery. So we have IA times RA, which is negative, and VA also a negative. And then we'll substitute what we know. For I, we can use the KCL that we've derived earlier so that we can easily solve for the unknown. Let's leave it like that for now and proceed with the bigger loop, which now involves these 3 circuits. Starting again with positive VG, negative IR, this one is negative IB times RB, and negative VB. Substituting the given values and also using the KCL for I. When we look at these 2 equations, we can use different algebraic techniques, but it will be easier for us by subtraction, so that these will cancel out. And turning the remaining terms to positive, so we'll get 0.51 times IA plus 108 is equal to 0.25 times IB plus 110. From which, if we solve for IA, we'll get IA is equal to 4 plus 0.5 times IB. This is now our third equation. So now we can substitute this to either of the equations on the previous one. So let's pick the second one. From which IB will yield 24 amps of current. Now we can plug this back to the third equation and we'll get IA is equal to 16 amps. And lastly, going back to our KCL, we have I is equal to 40 amps. For B, we are asked to look for the generated power PG using the formula P is equal to IV. That's 122 times 40 is equal to 4,880 watts. Now for letter C, that is the total power loss of each load, and so we'll use the formula I squared times R for each of the loads. So for the resistor, we know that the current I is 40, so that's 40 squared times the resistance of 0.15. For this battery, we got the current IA of 16 amps, 16 squared times 0.5 plus this battery IB has a current of 24 amps, so that's 24 squared times 0.25, and so we'll get the total of 512 watts. Lastly, for D, we are asked to find the efficiency rate using the formula 1 minus power loss over the generated power multiplied by 100. And then we'll get 89.5% efficiency rate.